This lab is on recrystallization. This should take you back to the concepts that you learned in general chemistry 2, that when you take a solute and you put it in a solvent, depending on the concentration and the temperature, if your overall solution remains unsaturated, nothing is going to crash out of that system. On the other hand, if your solution is saturated with respect to the solute, then a solid can precipitate out. What do we mean by that? Well, let's consider a hypothetical situation. Let's say you're making goodies for, during holiday season, and you picked up the last bag of sugar that was in the supermarket. And there's nothing else. No Publix or Target or Walmart has that. That was the last bag. And when you came home, maybe your dog jumped at you or something, and you got startled, and now that bag is on the floor. So it's basically a mix of dirt and sugar. And now the question is, do you want to make those goodies or not? Because you still need that sugar. What would you do? Now, the chemist in you should think of a solution. What can be done is you can put some water. Since sugar will dissolve in water and dirt will not, you can use water and basically heat it. The reason why you want to heat it is because you want to generate a saturated solution. So you want to concentrate it down. And when you will then recool so filter it to remove the dirt, and then recool it. And when you recool, you will see that in your vessel, sugar crystals will form. And these sugar crystals will be absolutely pure, devoid of any dirt, anything else other than sucrose. This is the concept that we are going to utilize in this lab. You would be given, between you and your lab partner, you would be given an impure sample. So we'll begin with an impure sample. Your first aim would be, so that's part A, your first aim would be to determine which solvent fits your system best, which solvent to use. And your second aim, which is part B, would be to quantitatively purify a given sample. It's the same sample. So as you come to the lab, I would assign, between you and your lab partner, I would assign you an unknown. Okay? You will first do a series of experiments to figure out the solvent that you need to use, and then you would use that solvent on the same unknown to quantitatively, when I use the word quantitatively, meaning you would use that on a 2-gram scale or a 3-gram scale. In this particular experiment, we are going to go with 2 grams, and you will try to purify it and report how much you were able to recover from it. Okay, so you will be reporting a percentage recovery at the end of the day. So let's talk about the steps as to what needs to be done. Let's talk about the determination of solvent, so part A. What you have to do is take 4 test tubes and fill one of them with 2 milliliters of DI water. Fill the other one with 2 milliliters of ethanol. Fill the third one with 2 milliliters of petroleum ether. Petroleum ether is nothing but a mixture of hexanes, isomeric hexanes. And the last one is 2 milliliters of toluene. So hopefully you can see that these are 4 different solvents. They have different polarities, and hence the way they will dissolve a particular compound or not is also going to be different. So for instance, you hopefully recall from chapter 11 in General Chemistry 2 and earlier this semester when we discussed the forces of interaction, and I made a statement. I said like dissolves like. Like dissolves like. That means if you have a polar compound, it would more likely go into polar solvents. On the other hand, if you have a non-polar compound, you're more than likely going to be able to use toluene and petroleum ether to be able to do that. Now, it's a possibility if you are not able to figure out your solubility in clearly one pure solvent, you might have to use a mixed solvent. But for the purpose of time and for the purpose of the amount of effort each group should put in, I will assign you compounds which do not require mixtures, but rather just one of these. Okay, so you don't have to worry about it. Just know that that's a possibility also. All right, you're going to weigh approximately 50 milligrams of your unknown in 4 different lots. You're going to put 50 milligrams of the unknown in the water test tube. You're going to make another measurement, put that in ethanol, make another measurement, put that in pet ether, and the last one in the toluene test tube. Okay, it's a good idea to put the weighed sample first, so that you are making sure that all of the solid kind of goes and sits at the bottom of the test tube, and then fill it up with the 2 milliliter solvent. It's a good idea to reverse the sequence basically, so that when you're doing the addition of the solvent, you do that along the walls if required. If there was anything stuck on the walls, everything kind of is washed to the bottom of the test tube. Now, also, if I were you, I would use the 6-inch test tubes because you have to heat these test tubes, and you really don't want to, have the solvent kind of boil over. We never want to do that. So make sure that you use the medium-sized test tubes, not the small ones. Now, what do we do next? You will be building up an observation table. As you write your pre-lab, you will be building an observation table in which, this is for the part A, you have your unknown number, and then you're going to say what happens when you put it in water, ethanol, petroleum ether, and toluene. Those are your 4 entries. You're going to say what happens when it's in cold, what happens when you heat it, and what happens when you recool it. Hopefully you realize that your aim is to look for a solvent which keeps the solid insoluble or partially soluble when it's cold, and completely soluble when it's hot. Because you want to ultimately get to a point where only the compound dissolves, the impurity remains insoluble, and you can filter it through, and when you cool it down, your dissolved compound should reprecipitate. That is the aim. So for your sample, you're going to make a call in terms of whether it will be one of the 3, whether your compound was completely insoluble, so it didn't go in water, or was it partially soluble, or was it completely soluble. It will be one of the 3. You have to make your call between you and your lab partner. If you think that you added 50 milligrams of the material and it still, stays ballpark the same, then you call it insoluble. Nothing happened to it. A lot of times you will see that the solvent and the solute are not interacting with each other, and you would see a clear indicator of that is that your solid is going to float on top of your solvent. On the other hand, if it tries to interact, it usually settles down, or the amount would lessen a little bit. So you have to eyeball to be able to make that call. Realize that if your solvent dissolves the material completely in cold, it's of no use to you. Why? Because if it's already dissolving your compound completely, it's not going to throw it back out when you try to heat it and then recool it. So you don't even have to heat it. On the other hand, if it remains insoluble or partially soluble, then you can subject that to heating. We heat it in a water bath. The water bath that you would make is using a beaker, so that goes faster. You can, if you want to, you can use the metal rings also. That's okay, but a beaker will be faster in this case. And you will use that to figure out what happens when you heat the sample. So as you heat the sample in the water bath, you will then make a call, your judgment, as to what happens. So let's say water, it was insoluble, and when you heat it, it started to go in. So it becomes partially soluble. And in this case, in ethanol, it was partially soluble, and now it's completely soluble. Completely soluble. And now when you recool, so that means you would be putting this in ice, you would then see what happens. Maybe this remains completely soluble. Nothing crashes out. And maybe the one for water crashes out completely. So use water as your solvent. On the other hand, if the ethanol one actually crashes out completely, a lot more, then that is the solvent that you want to choose. But underneath the table, you would say solvent choice. And whichever solvent you're going to use, you can state that. Okay, so that's your first observation table that you're going to use. Again, quick recap. Approximately 50 milligrams, doesn't have to be 50.000, could be somewhere around 48.253, 53.124, whatever it is, somewhere between 45 to 55, ballpark in the same range. You should know how much you took. But we are using 2 milliliters of solvent. This is basically a qualitative assessment. This is a qualitative assessment of all solvent choices. All solvent choices. In the next step, we have to figure out how much can we recover if we use this solvent choice. So that's my quantitative actual recrystallization technique. So that's the next thing. In order to do this, you will start with approximately 2 grams of your material. So you have to give me the mass of the weighing paper. You should find that out before you tear it. Whatever that is, write it down in your notebook. Mass of weighing paper plus the unknown, whatever unknown you have been given. You're going to take approximately 2. Again, it doesn't have to be 2.000. Somewhere between 1.9 and 2.1 is a good number, but you have to record the exact numbers. And then, of course, A minus or B minus A, that will give you C. B minus A, that will give you C. So you have to know how much you're transferring. You will take that in an Erlenmeyer flask, 50 milliliter Erlenmeyer. You're going to put your unknown, and you will add about 10 milliliters of the solvent that you had chosen from part A. From part A. You are going to now heat it in a water bath or a steam bath. We are going to do, by the way, everything in the hood, because we don't want to inhale any vapors. So we are going to do everything in the hood. So as you heat it, you should see that a lot of the solid starts to go in, and it should completely dissolve, or at least some amount should get reduced. Now, realize that as you're heating, it's a possibility that some of your compound will tend to crash out, because it's a very quickly you're removing some of the solvent. As it's heating up, it's getting evaporated as well. So what I want you to do is add 20% more of the solvent, because realize the amount that goes in will be dependent on the amount of solvent that you have in there. Because if you don't have much of the solvent, you have utilized all the solvent spaces for the solute, and it's not going to go in. So if you started with, let's say, 10 milliliters, you can add up to 2 milliliters more and then reheat it. As you reheat it, you will probably realize that it should, again go in, and that's a good thing, because you want to maximize your percentage recovery. You want to make sure that in the beginning a lot of your compound goes in. You don't want to add too much, because you want to keep the solution saturated, or as close to saturated as possible. Now, as you heat it in the steam bath or water bath, as is applicable to your particular system, you will see that a lot of the solute will go in. It's a good idea to put a boiling chip in here as you are heating that, because boiling chip prevents heat cells. And it allows uniform heating. So the liquid within your system would not, just explode. So it's a safe way of heating. Now, when you're satisfied and you see most of your material has gone in very, very quickly, and this is something you have to, between you and your lab partner, you have to find a way so that one person is watching the concentration being done, the reduction of the solvent being done. The other person is maintaining and getting the stemless funnel system ready. So what you're going to do is you're going to bring in your, let me make some room here. You're going to bring in a stemless funnel and an Erlenmeyer flask. The reason why you want to use a stemless funnel is because if you had a stem, then all of your solid is going to start to crash out within that glass funnel, and you don't want that. You don't want premature recrystallization. You want it to make it through the filter and crystallize here in the flask. So what you're going to do is you will take a filter paper. You will first make a semicircle out of it. Past that, you're going to make a quarter, so you will get semicircle first, and then you're going to make a quarter out of it, so it will look like this. And basically use one of the edges, much the same way you did that in Gen Chem 1 or Gen Chem 2. So it looks like a cone, like a birthday hat. And you're going to put that into your funnel. So let me just switch the color to show you how that would look like. And what you will then do is, if you don't actually use the solvent to hold it, it is going to fly away. So whatever was your solvent of choice, let's say it was toluene, I want you to add a little bit, just about 1 to 2 milliliters of the solvent onto that funnel, or this filter paper rather, so that it kind of sticks to the filter paper, or to the funnel, and it doesn't fly away. And when you're ready, absolutely, pour down your Erlenmeyer flask, pour down your liquid through there. You will see as the liquid sees the cold filter paper, it will tend to crash out. That is going to happen. So you will lose probably a little bit of your recovery there. And you can, if time permits, you can go for a second crop, if time permits. If not, then we'll just live with it. So you will see that your liquid will go down and it will immediately tend to crash. If it does not, then we are just going to cool it in ice. Cool in ice for at least 10 minutes. And then you should see a solid, and your aim then is to filter it on a Buckner funnel and get a melting point. So what you'll then do is set up a Buckner funnel. You are supposed to clamp it. So we'll set up a filtration funnel. It has two parts. Which, if not constrained, if not put together, and if you don't use your index finger to hold it, it can fly away. So what I want you to do is take the Buckner funnel, put the small filter paper on it, and I'll show that in class as well very quickly. And you're going to put in whatever had crashed out, you're going to put that now through this. So when you filter, only the liquid goes through, the solid should settle on your filter paper, and that's what you're going to collect. You filter through a vacuum, because you want to make sure that it is nice and dry and ready to be taken a melting point off. Leave it at vacuum for about 3 to 4 minutes, and that's usually plenty to get rid of all the solvent. If I were you, I would not use a sharp spatula to, keep touching the filter paper, because realize it's going to be moist, and if it's moist, it's going to be very tender, and it can tear, and some of your material can go through. Your percentage recovery will suffer then. So I would gently, with a very light hand, if after 3 to 4 minutes, just kind of, see from the side if it seems dry or if it seems cakey and chunky. If it seems a little bit chunky, give it another additional 1 to 2 minutes. But if it seems dry, then that should be good to be used for the melting point. You already know how to take the melting point. You have to make sure it's a powdered sample and it is packed well in the capillary tube, and then you'll take at least 2 melting points to see if your compound is one of the 4 that I have mentioned in the student notes. Now, one thing that I would say, before you proceed towards the melting point, it's a good idea to transfer your material on a watch glass, a pre-weighed watch glass, and get your percentage recovery from there. So what you're going to do is you would say mass of watch glass. I just don't want you to tear that. I want you to write it. Whatever is the grams. And then you say mass of watch glass plus compound purified compound now, recrystallized compound, whatever grams you get, and then mass of watch glass when you subtract A, B, C. This will become mass of recrystallized compound, however many grams. So B minus A will give you C. You will also write here what you began with. So mass of impure compound taken. So that's the number that you had taken before recrystallization. So that's the number which is approximately equal to 2 grams, whatever that number is. And then you will have a percentage recovery, which can be calculated as what you purified, so what you recovered, divided by total impure compound taken, times 100. So let's say you were able to recrystallize out about 1.201 grams. You would say 1.201 divided by 2.000 times 100. Or let's make this number actually a different one, so you don't think that it is going to be 2, but what you got, 1.953. Maybe that was the number that you had. So you would just get the pure number divided by the impure number times 100, and that will give you your percentage recovery. Once you have that, get the melting point. So that will be the last thing that you will do. Take the melting point. The melting point, like I said, is going to be a range. I really prefer 3 melting points, but at this point of time, it really is a question of time, how much you have. Let's say you are able to get 3 melting points. The first one came out to be maybe 90 to 93. The second one came out to be 91 to 93. The third one came out to be 91 to 93.5. Then the average is going to be all the lows put together. So that will be 90 plus 91 plus 91 divided by 3. So all the lows together to all the highs together. 3.5 divided by 3. So it has to be a range as well. And now you will write down your conclusion, which will include everything right from the beginning. So you would say unknown whatever was recrystallized in whatever it was your solvent of choice, in whatever was percentage recovery. You will discuss that, and you will say that we identified this, or not using the we, you would say it was identified to be what you think is the identification based on the melting point of, and then say the average melting point. So whichever it's closest to out of those 4, you would say that that is the identity of your unknown. That is the lab. All right, I'll see you in class.